Hello. All right. So I'm Michael Nelson. We have the members of our committee here: Michelle, Michael, Elizabeth Vincent, and Erwin is also a member of the committee as well as the Donut Man. So most of you know Justin. He's been around in the department for forever, and this is probably the only dissertation that you'll ever see that references Samuel L. Jackson. So with that, we'll let Justin get started.
So Samuel L. Jackson got a shout out in my acknowledgments in the actual written dissertation as well, but that's not important. My name is Justin Brunelle, and I'm going to be defending my dissertation entitled Scripts in a Frame, a two-tiered approach for archiving deferred representations. And before I get started, I do want to thank my committee for putting up with me forever, as has been mentioned, especially my co-advisors, Dr. Nelson and Dr. Weigel. And I also want to thank my wife, June, who's in the back, for not murdering me while I wrote it. So back in the good old days of the web had a much simpler structure than it does now. In the web, we have these things called URIs, Universal Resource Identifiers, that identify web resources. And these web resources have representations. And these representations are things like HTML pages, they're JPEGs, they're text files. They're the things that we're familiar with interacting with on the web. And back in the good old days, it was very easy for our archival tools and web archiving crawlers to archive these representations and make them available for us to see in the web archives. However, there's been introductions of new client-side technologies and client-side programming languages such as JavaScript that make archiving these representations much more difficult. And that's because our browsers have to be able to execute these programming languages in order to render a final representation on our clients. And the web archiving tools that are used for web-scale archiving do not understand how to execute this JavaScript, and therefore we see some funny things and some bad things happening in our archives. So I've mentioned that the web archives are doing things like archiving these representations, so it's useful for us to establish sort of a common understanding of what these archives are doing. And in this case, we've got three archival institutions on the right: Internet Archive, archive.is, and Archive.it. And I'll talk about how these are a little bit different later on in the presentation, but just keep in mind that these are all archival institutions that are capturing and archiving representations on the web. And we also have CNN.com, and everybody knows CNN.com, and this is the CNN.com homepage. And we also all know that CNN.com changes over time. They publish new stories, they change the layout, they change the content, they update with breaking news. And so we see that this information changes as time progresses. And as time progresses, these archives are going out and capturing versions of CNN.com that we refer to as mementos. That is, each of these archives has mementos of CNN.com over time. And what they're doing is being able to capture those client-side states in the archives for us to view and see what CNN.com looked like in the past. So I mentioned that the introduction of JavaScript is causing funny things to happen in our archives. And in this case, we're going to take a 2008 memento of CNN.com as it exists in the Internet Archive. And we can tell that it's from the Internet Archive from that bar at the top. And in this CNN.com memento, we'll note that Sarah Palin is going to be running for the vice presidency in 2008. And in the bottom right-hand corner, there's something missing in that memento. And it's supposed to be an online advertisement. And that online advertisement is missing because when the archival crawler, in this case Heritrix used by the Internet Archive, showed up to archive the CNN.com homepage, it didn't understand to execute the JavaScript that is responsible for pulling in that advertisement into the page. And therefore, when we view this in the archives, it's missing. And so this is bad because now we have an incomplete memento in our archives and we don't know what should have been there. However, it gets way worse because, again, we have another 2008 memento, and in this case we've got an article about Palin and McCain in the Republican National Convention, and we have the same area in which online advertisements are loaded, but in this case when the JavaScript runs in this memento, and when we view this in the Internet Archive in 2012, at the time that we observed this memento in the archive, there was another presidential race going on between President Obama and the presidential candidate, Mitt Romney. Unfortunately, President Obama at the time of archiving this page was not yet elected president. So what we have here is the JavaScript executing, going out to the live web and pulling in a live web advertisement And what we have is a seemingly prophetic look at the future in this memento. And that's all because the archival crawler that was responsible for creating this memento didn't understand how to execute that JavaScript and understand what to do with this. And so we call this a temporal violation, which is worse than a missing embedded resource because it presents a live web thing as if it were archived. And you might be saying, well, Justin, people actually write software to prevent advertisements from loading in web browsers. So we think they're annoying and they're terrible and they should all go away and never come back. But old ads are actually interesting. And so if we look at old ads from magazines, we find these very interesting because they provide an unfiltered and unedited look at social norms of the time. And so I took some humorous ones like doctors telling us to recommending that we smoke cigarettes, and then we've got sexist ads. And my favorite is we want to wrap our babies in cellophane to make sure they stick around forever. So when we look at what modern ads look like on the web, we see some different types of things that might be indicative of social norms of today's society for future historians and scholars and researchers. Some of them are boring, like, okay, well, we're a device-centric society and we're going to pay $300 for a tablet. Others are ironically juxtaposed with the content because we have a teacher being hit by a car and then an ad for Toyota popping up, which is unfortunate. And my favorite is the one in the top right corner. You have two boys looking at a camera and saying, "Why are your parents wrestling?" And this is interesting to me because in the spectrum of society and in history, sexting is probably not going to be very prominent. But this shows that in today's society, this is something that's prominent and ubiquitous, and that it can be a problem if your kids get a hold of your video camera. And so, as I mentioned, a lot of these advertisements are served by JavaScript. And so if we take this big nasty URI of one of the advertisements at CNN.com and ask the Wayback Machine at the Internet Archive to give us a prior version or a memento of this advertisement, we can see that the Wayback Machine says, well, I don't have one of those. I don't have that archived. But it is available on the live web, and we can start trying to archive that for you right now. And the reason that this is not represented in the archives is when the crawler showed up at CNN.com and tried to create a memento of it, it did not execute the JavaScript, did not construct this big nasty URI, and therefore could not understand that it was supposed to archive it. So sure, okay, you might be saying, well, advertisements suck, I don't care about them anyway, and if we get the main content and all the other good stuff, well, then what's the big deal? So we miss a couple of advertisements. But there are situations in which historical events are actually being completely lost from the archives. And for this example, we refer to the Stop Online Piracy Act. So everybody might remember back in 2012, about January 2012, the US government tried to pass the SOPA Act, or Stop Online Piracy Act, and it was widely unpopular with all of the major content providers, and in response, they organized a big protest. And while the attempted passing of SOPA may not be particularly interesting or historically noteworthy, the overwhelming protest and response is something that is historically significant. And if you went to Wikipedia during that time, on January 18, 2012, this is probably what you saw. Wikipedia blacked out its content and made it unavailable to web users as a way to protest the attempted passing of SOPA. And the way that they did this was they embedded some JavaScript in their representation, and that JavaScript went out to the web, pulled in a big splash page, and that splash page covered all of the information and blocked access to that content. However, if you look at a memento from January 18, 2012 of wikipedia.org, this is what you see. You don't see any mention of the splash page, and actually you see in the HTML they're saying that, yeah, guess what, we're blacking out our content to protest SOPA, but we don't see what we saw when we were visiting that page live. And again, this is because the archival tools didn't understand how to execute that JavaScript and didn't understand to archive that splash page. And therefore, without the human curated efforts of people that thought the SOPA protest would be historically significant, this is an event that we wouldn't have represented today. Whoops. So this really boils down to a fundamental problem, and that is the tools that we're using to archive the web don't behave like users that are browsing the web. And in this case, we know that Heritrix in the prior examples, that tool is not behaving like a web user. And as a result, what we're finding is that the web archives are containing a view of the web from the point of view of a web crawler, rather than a view of the web from the point of view of the web user. And getting to and a more fundamental question is, well, why are we archiving anything at all? And clearly the Internet Archive has everything. We all know that they've solved the problem of archiving, so we can all go home. And further, it's the responsibility of the content and website owners to back everything up and then turn that information over to the web archives. And further, you should just be able to back up your database and be able to replay this information as needed. And these are common misconceptions about web archiving that we will demonstrate are frankly incorrect and debunk them through the Crimean conflict example. And if everyone remembers, back in 2014, Russia invaded part of the Crimean region of the Ukraine and annexed it. And at the time, the Crimean Center for Investigative Journalism was publishing articles online on their website that painted the Russian invasion in a negative light. And the Russians decided they didn't like this. They sent a bunch of masked gunmen into the Crimean Center for Investigative Journalism to take down the servers and stop posting that content. And during that takeover, the gunmen are actually recorded on video as saying, "We will try and agree on the correct and truthful coverage of these events." So if we think about our, what that means for the history, that means that all of that information is now being taken down. But the Archive It service, and Archive It is a subscription-based archival service that allows humans to curate the content that's being archived, to archive information. And in this case, they thought the Crimean invasion was historically significant, and they were actively capturing mementos of the Crimean Center for Investigative Journalism's website. And we can see one of the mementos that they captured here. And if we revisit some of those myths about web archiving, right now your backup servers are controlled by masked gunmen. They're on the servers that they've just taken over. Also, you don't have your databases because those are also on your servers and under somebody else's control. So the only way that we can effectively and actively archive this information is by third-party access over HTTP, which is why we archive the web in the way that we do. Also notice that, again, in the bottom right-hand corner of this memento, we have a missing embedded resource. And this embedded resource should have been a video loaded by JavaScript, demonstrating further that even when actively curated by historians, the tools that we're using to archive the web today aren't capable of finding things that are dependent upon JavaScript to load. So this is important because the web is a ubiquitous part of today's society. It is the primary publication medium of today, and it is the primary way in which we communicate with each other. So it's very important, and therefore any future discussion of the 21st century is going to have to talk about the web. And because the web archives are the primary record of the web in today's society, any future discussion of the early 21st century has to talk about the web archives and use the web archives. However, as we've shown through the prior examples, JavaScript is hard to archive, and it's making the web archives ineffective at what they're doing. And as a result, what we're seeing is archives from the point of view of web crawlers rather than from the point of view of web users who are actively using the web. So that brings us to the goal of the research that I'm talking about today, and that is we want to understand the best way to mitigate the impact of JavaScript on the archival tools and therefore the archives. And we want to do this by allowing them to behave more like the web users that are using the web rather than the crawlers that are archiving. So now that everyone understands that we're doomed to never see another web advertisement again and all hope is lost, we're going to go into a little bit of background information about why this is a problem and a little bit about the web in general. And then we're going to move into the research questions that are presented en route to the solution that we proposed, followed by some future work and conclusions at the end of the presentation. So I've mentioned some of these archival institutions before in this presentation. We talked about the Internet Archive, which is the big one. The Internet Archive is chartered with trying to archive the entire web, even though it can't feasibly do that because of issues with scale. And then we've got Archive It, which is associated with the Internet Archive, which is a more curated service that is a archive by service type of archive. And then we have more specialized archives that exist. And these are things like the national libraries that are responsible for archiving all of the websites within their national domains. So we also have different types of archivers that aren't these automatic web-scale archives as well. We have things called page-at-a-time archivers. And a page-at-a-time archiver is where a web user can recognize that, hey, this is an important resource. I want to submit the URI to the page-at-a-time archiver, and it will archive it once for that user. So this is sort of on-demand archiving. And we have a website, which is a page-at-a-time archiver, as well as archive.is, which I talked about previously. And archive.is actually does a really good job at archiving pages that rely on JavaScript, and I'll talk about why a little bit further into the presentation. But we also have Mummify, which was a page-at-a-time archiver service that is now defunct, and it also demonstrates that not only are these web pages ephemeral, but we also see these archives die as well. And we also have archiving tools that we can use. And Heritrix, that's used by the Internet Archive, which is their web scale crawler, is open source, and you can download it and use it. And you can also use something like wget, which is a command line tool that downloads a representation and all of its embedded resources onto the client. And from the subsample on the page, Matt Kelly is responsible for developing about 50% of all archiving tools. And he's responsible for the WarCreate and Whale tools that I highly recommend you talk to him about using for your own personal archiving purposes. So we sort of understand that there's all these different archives, everybody's creating mementos, and this is where we get into the memento framework. And the memento framework facilitates the process of not only navigating spatially in the web, that is from page to page, but also temporally, meaning from a page to mementos of that page and going back in time. And the way that it does this is by establishing a machine-readable bidirectional link between the past and present webs. And it does this through what's called the accept datetime header. And by providing this header in HTTP, you can actually specify which date of that resource that you want to see, and Memento will give you the appropriate or most appropriate memento for what you're looking for. But in the context of this presentation, the way that we're going to talk about memento is a little bit narrower. What we're going to talk about is the memento aggregator, and if you give the memento aggregator a URI of a resource that you want to see a memento of, it goes out to all of the known archives that it has knowledge of, gets all of the mementos from those archives of the resource that you're looking for, and presents to you the most appropriate version of that, most appropriate memento of that resource to you. And as part of the memento framework, we have some terminology that allows us to talk about web archiving a little bit more easily. For example, we have a URI-R, and that is a URI that identifies a live web page. So it's basically the original resources identifier. We also have URIs for mementos, and those are URI-Ms, and what these are identifiers for the archived version of that page. And finally, we have something called a time map, and a time map is identified by a URI-T, and a time map is a machine-readable list of mementos of a particular resource. So if we go back to the first slide that I had and talk about the web architecture, the way that we as users browse the web is by using our web browsers. And what's happening behind the scenes is our web browsers are issuing HTTP GET requests to a server for a particular URI. And remember that URI identifies a resource, and that resource has a representation. And so what happens is that server takes that request, that HTTP request, and it responds to our browser with an HTTP 200 response if it finds that web resource, and along with that comes a representation. And then our browser does some rendering of that representation so that we as humans can read it. And this process is called dereferencing. So when our browser dereferences a URI, it gets back a representation. And this was the extent of the process before we had introduction of client-side tools like JavaScript. And when JavaScript was introduced, we had a little bit more of a complex process that happens. In this case, we're going to consider Google Maps. And the Google Maps has a URI-R maps.google.com. And Google Maps also has a representation. Now, the representation for Google Maps is actually just an HTML sort of container with a bunch of JavaScript embedded in it. And that representation, that HTML frame and JavaScript is given to our browser, and that browser will execute the JavaScript code, and that JavaScript then is responsible for issuing new HTTP GET requests to a Google server somewhere for all of the map tiles that get populated in Google Maps that give us the end representation that we as humans expect to see from Google Maps. So we call this a deferred representation. And we call it a deferred representation because the representation is not completely built out and completed until after JavaScript runs and issues these additional HTTP GET requests and receives those additional embedded resources. And as I've mentioned, these deferred representations are really what cause problems for the archives. It's worth noting, though, that just the mere presence of JavaScript does not mean that something will be deferred. So we have two classes of representations, non-deferred and deferred. And non-deferred representations, things like just pure HTML are clearly not deferred, but things that include JavaScript are not necessarily deferred. For example, if we consider the cs.odu.edu homepage and go to Michael Nelson's faculty page, at the bottom there is this link that says click here to unveil his phone number and click here to unveil his email address. And if we click those, JavaScript is changing the local representation, but it is not issuing additional HTTP requests for this information. That's because all of that information is stored locally on our browser before we click that button, and therefore it doesn't need any new information in order to reveal his phone number and email address. However, Google Maps is deferred because it's relying upon JavaScript to reach out to a new server through additional HTTP GET requests and bring in those map tiles that are responsible for basically giving us the representation that we as humans expect. So now that we all understand how JavaScript works, it's useful for us to go revisit the entire web browsing process. So as I mentioned, we start off with our browser issuing the HTTP GET request for a resource or with its URI R, and then the server that handles that request issues a response along with the representation. Our browser takes that representation and renders it for us and executes the JavaScript, at which point that JavaScript might be making additional requests for embedded resources. And that might be to a new server. And that additional server will respond with new embedded resources for our representation. And at this point, we can have user interactions, we can pan, we can zoom, we can click, all that kind of stuff. It's also worth noting that we don't necessarily get the same representation regardless of the environment variables that influence it. So I like to say that we no longer have the representation of a web resource. We no longer have a single representation. What we have are a representation that a user might get at a certain point in time. And that's because of the environment variables that are associated with how the server responds. For example, I know we've all been in different locations. For example, if we're up in Washington, D.C. and go to Weather Underground, we don't get just a weather. We get the weather for the Washington, D.C. area, which is different than at the same time if I'm at my house in Suffolk and I go to Weather Underground and I get the weather for Suffolk. These are clearly different, and they're different because my GeoIP is telling the server where I'm located, and it's giving me different weather dependent upon that GeoIP. But this all doesn't matter because the Internet Archive has solved web archiving, and we should all go home. And if you look at the time map from the Internet Archive of Google Maps, you can see that it appears that Google Maps has been well archived over time. They've got lots of mementos of it. But if we click on one of these mementos, what we see is something very different than what we expect. What we're seeing here is a memento that is not interactive. We can't click, pan, and zoom. And it's also missing map tiles. So the reason that this is all missing is because while the Internet Archive has archived the HTML frame, it hasn't executed the JavaScript and therefore hasn't archived the map tiles that are responsible for being in this page. The reason for all of this, again, is because each of these tools stops at a certain point in our web browsing process. So, Heritrix and the website wget tools, all they do is they dereference a URI, get back the content, and then archive that representation. And we can execute JavaScript on the client using headless browsing tools. And an example of a headless browsing tool is Phantom.js, and Phantom.js is used by archive.is to make sure that it gets all of, some of the embedded resources that are required to archive that representation, even the ones that are reliant upon JavaScript. But the problem is this process of users interacting with, clicking buttons, panning, zooming, and updating a representation on a client is still not something that's solved. This isn't solved by any of the archival tools we've covered. And that's where our research starts to make an impact. So starting with a couple of research questions that we asked en route to our final contribution, first we want to understand to what extent JavaScript is impacting these archival tools and as a result impacting the archives. And given that we sort of intuitively understand that JavaScript is having a negative impact on the archives, we want to have a quantitative metric of quality to be able to measure how bad that impact is. And finally, the real main contribution of this research is we want to identify a method for crawling, archiving, and then playing back these deferred representations. So starting with the first research question, this really gets into the work that we published in DLib magazine, TPDL in 2013, and in the International Journal for Digital Libraries in 2015. So if we go back to our Palin example here, we can see, we know that this is a 2008 memento that reaches out into the live web and pulls in some 2012, at the time of observing this memento, pulls in some 2012 embedded resources. And we call this a zombie because zombies should be dead and should be interacting with the live web, or the live world, and just like this should be an archive memento that should be interacting with the live web. And he's just like our buddy Vigo over here, who should be coming out of his painting and interacting with us. And we refer to this phenomena of reaching out into the live web and pulling in archived or live web resources as the live web leaking into our archives. So we wanted to figure out the extent to which leakage occurs in the archives. And to do this, we set up an experiment in which we sampled 1,000 URI-Rs from Twitter, the URIs that were shared over Twitter, and 1,000 URI-Rs that were represented in Archive.it, and we captured them with 3 different archival tools: the website page to time archiver, the wget command line tool, and then the Internet Archive suite of tools, which is archiving, crawling with the Heritrix crawler, and then viewing those mementos in the Wayback Machine. And what we found were the results varied. So we had some mementos that were well preserved, like when we view this resource on the live web versus as it appears in the Wayback Machine versus how it appears after we download it with wget and look at it on our local host machine. All of these look about the same, so we can say this is well archived. However, we see other things that aren't necessarily as well archived, but aren't necessarily bad either. So in this memento, we see that we have, or in the live web resource, we have a bunch of social media like icons and share icons and things like that. But when we look at the memento from the Internet Archive, all we have left is the like icon. So that means that the Internet Archive didn't capture any of the other icons. And website's even worse because it doesn't have anything at all. But the real interesting thing happens when we look at what on localhost or wget downloaded onto this machine, and when we view it on our localhost machine, we only see the Facebook like icon, which looks a whole lot like what the Internet Archive got. But what we did next was we physically unplugged the Ethernet cable from that machine to prevent reach into the live web. And what we see when we look at that memento again is that Facebook like icon is gone. That means that that like icon was a function of leakage. And so by disconnecting that Ethernet cord, we prevent the zombies from coming into the live world. And then we have things that are way, way worse. If we look at Perez Hilton on the live web, we can see, okay, you've got a bunch of pictures and images, and when we download it with wget, you still have your pictures and images, and so it looks like it's archived okay. But when we unplug that Ethernet cable, all of that disappears. That's because all of that information is loaded by JavaScript and is a function of leakage when we view it in these mementos. And we can see that, even in the website memento, we still have some leakage that occurs. But even worse is when we look at what happens with the Internet Archive. During the crawl, some of the JavaScript was corrupted, and we see something that looks nothing like our live web representation. So if we consider our collection as a whole, and consider the performance of our collection as a whole, we showed that the Twitter data set that we had actually has more leakage when archived than does the Archive.it section. And that's because that could be from a couple of different reasons. It could be because the things that users want to share on social media are interactive and therefore more interesting, or it could be that Archive.it has more government-centered websites that traditionally avoid JavaScript. But the punchline here is that Twitter has less leakage than the Archive.it set. The other thing to note here is that the Heritrix and Wayback combination limit the leakage the most in our archived collection. So in other words, Heritrix is doing the best job of limiting the leakage that we see in the mementos. And what we did next was we sampled from 2005 to 2012, at the time of the study, the mementos of our 2,000 URI-Rs and identified which of them were using JavaScript to try and pull in embedded resources. And what we saw was from 2005 to 2012, we saw a 12% jump in the number of mementos that were using JavaScript to load embedded resources. And as I mentioned before, we understand that JavaScript leads to potential for leakage. We actually see a correlation between the increased adoption of JavaScript to load embedded resources as we do missing embedded resources over time in this collection. And to look at that another way, again, considering 2005 to 2012, if we consider everything in that observation period that we saw was missing from the archives, about 73.1% of it was missing because it was reliant upon JavaScript. That means almost 3/4 of everything that the archives that we observed were missing because of JavaScript. And just to look at sheer numbers, from 2005 to 2012, we saw a 33% jump in the number of missing embedded resources in our mementos. So this means that the archives are having a negative impact from JavaScript, and we wanted to be able to measure the impact quantitatively. And we wanted to, and this reflects the work that we presented at DL 2014, and that won Best Student Paper, and we were invited to a special issue of IJBL in 2015. So recall the two mementos that we used in our example previously. Clearly missing a few Facebook-like icons is different than missing all of the content. So we want to be able to understand the differences between these and automatically measure the quality. So because we're all good computer scientists and look at XKCD all the time to laugh at funny comics, we consider XKCD as an example, and even when live, XKCD is missing 17% of its embedded resources. And to demonstrate a point here, we created a memento of XKCD and consider 3 different embedded resources from that representation. We consider the logo at the top, we consider the main comic in the middle, and then we consider this navigation strip down at the bottom, which is a single image. And if we start to remove some of these embedded resources, we can see that by removing the logo and the navigation strip, we're now missing 29% of the embedded resources in our XKCD memento, but because we can still see a funny comic and laugh at it, we don't care. We can say that this is still something that you would visit in the archives and get what you came to visit the page for, and that is the funny comic. However, if we put back those 2 smaller resources and take away the main comic, we're now only missing 24% of the embedded resources, but now we can't laugh at a funny comic, and we as humans will say, well, this is not a usable memento, demonstrating that the naive metric of just the proportion of missing embedded resources is actually not a very good metric for assessing the quality of a memento. To rectify this, we want to come up with a metric that will align closer to human perceived quality of a memento. And to do this, we consider a couple of different features of these embedded resources en route to finding that metric. So for images, we consider the size of the image, and that is the proportion of all of the pixels that image takes up on the page. We consider the position of the viewport, meaning did the content author decide that this was important enough for you to view immediately upon visiting that memento or that resource. And finally, we consider the centrality. Does it appear in the middle of the page, or is it put off to the periphery on that page? And again, this is a decision by the content author. And all of these different factors go into assessing the importance of that image and its importance to the page. Now, originally we didn't think that cascading style sheets or CSS was very important because we still have all of our information. Who cares if it's pretty? What we found when we started to do this experiment was the users care. Like everybody that's not an archivist cares. So as a result, we went back and revisited our metric and decided to have a metric for style sheet importance as well. And we've all seen this. When we're missing an embedded style sheet in a representation, all of the content shifts down and to the left, and it looks like the image on the right. So the way that we identify an embedded style sheet as important is by dividing the representation into vertical thirds and figuring out what the background color of that representation is using the remaining DOM and remaining style sheets, remaining document object model. So after we've identified the background color, we consider the non-background color things to be content. And we go pixel by pixel in these images and figure out where the content falls in each of those vertical thirds. And if a style sheet is missing and more than 80% of the content appears in the left third, the leftmost third, we consider that style sheet to have been important to the representation and organization of that information. So again, all of this goes into our damage metric, which we call D sub n, and we call the naive metric of the percent of missing embedded resources M sub n. And D sub n is really, when you think about it, a weighted version of M sub n. And to assess the closeness of our metric to user-perceived quality of mementos, we performed an Amazon Mechanical Turk experiment in which the Turkers represented the web users. And we did 2 legs of this experiment. The first leg is where we presented the Turkers with an image of a live web resource and an image of a memento that we created and removed the important embedded resources from. And in the second leg, we presented 2 sampled mementos from the Internet Archive to the users and asked them which one was archived better. And the results of our experiment show that about 80% of the time, when presented with a live web version and an archived but clearly damaged version of the same resource, about 80% of the time, the Turkers were able to identify the live web resource as the better one. Now, when we sampled the 2 Internet Archive resources, or mementos, they were only in agreement with our damage metric about 58% of the time. Now, that may not sound very impressive, but when you consider that they only agreed with the naive metric of percent of missing embedded resources 47% of the time, it actually provides an improvement over that M sub n metric. And this is even more impressive and important because when you consider that you have a 50-50 chance when you flip a coin, you actually have a better chance of agreeing with and assessing quality closer to user-perceived quality when you flip a coin than if you were to use missing embedded resources as your metric. And by the way, missing embedded resources is the primary metric used by the archives to assess memento quality today. So using our newly minted damage metric, we decided to measure over time the quality of mementos in the Internet Archive and website. And what we noticed was there was a spike around 2005 in the damage rating that we were measuring. And in 2005 is when JavaScript and Ajax were made popular to load embedded resources. So we decided to measure the difference between non-deferred and deferred representations in the archives and showed that deferred representations have a 13.5% higher damage rating than their non-deferred counterparts, showing that these missing embedded resources caused by JavaScript are actually having a very negative impact on the archives. And this is where we get into the heart of the contributions of this dissertation. And this represents the paper that we published in iPres in 2015 and a newly released tech report in Archive. So in order to understand what we propose to solve this problem, it's useful to understand how the archives are doing things now. So the way that archival crawlers work today is they have a seed list or initial crawl frontier from which they select a URI-R. They dereference that URI-R to get back that representation, and they extract all of the URI-Rs for embedded resources and other links from that representation and add them to the crawl frontier and iterate through that crawl frontier until it's empty. What we propose is a 2-tiered approach to crawling. And in this 2-tiered approach, we start out the same way. We start out by selecting something from our crawl frontier, we dereference it, and we get back a representation. Now what we want to do here is, as we've talked about, the traditional pipeline of archiving is actually suitable for non-deferred representations. So if a representation is going to be non-deferred, we want to send it through that same pipeline that it would normally go through without our 2-tiered approach. However, we use a classifier to understand whether or not a representation will be deferred to send it through a second tier of crawling. And in that second tier of crawling, we're using Phantom.js to dereference that URI and identify the interactive portions of that representation. And we use Phantom.js to then start clicking on things and to start mousing over things and understanding what new embedded resources are going to be required because of those types of user interactions. And all of that gets added to our crawl frontier. And as a result, as you might imagine, we're getting a more complete crawl frontier, but we're also taking a lot longer to crawl. And so we wanted to understand what that performance trade-off looked like and what the extent of that performance trade-off was. So again, we organized an experiment in which we sampled 10,000 URI-Rs from the web, and we crawled them with 3 tools, the Heritrix crawler, Phantom.js, and as a baseline, we crawled them with wget, and we measured the completeness and the size of the crawl frontier, which represents the completeness of the crawl, and we also sampled the crawl time. And what we've shown, again, using wget as just a baseline here, we showed that Phantom.js creates about a 1.5 times larger crawl frontier than does Heritrix, meaning that Phantom.js is finding more stuff and therefore crawling more completely than Heritrix does. However, it's a whole lot slower. It's about almost 10 times slower. Heritrix, which crawls about 2 URIRs per second, is a lot faster than Phantom.js, which takes about 4 seconds per URIR to crawl, meaning that Phantom.js is crawling a lot slower than Heritrix. I mentioned before that we have a classifier. Right now, consider it a magical black box. If you want to understand a little bit more in depth of how it works, you can refer to section 7.4 in the dissertation, but I'm not going to get into it here for the interest of time. So I mentioned before that we're training Phantom.js to understand the interactive portions of a page and interact with these representations. And we refer to the end states reached by interaction descendants. And if we go back to our Google Maps example, once we start at this root of Google Maps, we can do a different set of clicks and pans and zooms to get to different areas of the country. And so by using different interactions, different types of interactions, we can actually end up with 2 end states and 2 end representations here. And we also need different embedded resources in the map tiles in order to be able to represent those pages. So again, we call these descendants because we organize these states in a n-ary tree, meaning we have a tree of states that we can reach, and these states are each of the descendants, and these descendants are reached by a different set of user interactions. And because no PhD dissertation is complete without a finite state machine, we use a finite state machine to represent these trees. So basically, each of the states is a descendant, and each of the edges is an interaction that we need to execute in order to reach that state. So as an example, we'll consider Bloomberg.com. And up in the top here, if you visit Bloomberg.com, there's actually a menu bar that has a bunch of mouse over events depending on which of those menu items you mouse over. And so if we mouse over one of these things, we get a new menu bar. And we get the new menu bar because JavaScript is going out and getting some images and some JSON information that is required to build out that new menu bar for us. But that new menu bar has items that you can mouse over. And if you mouse over those new menu bar items, you get another set of AJAX requests that return JSON and images. And now we get things like stock tickers and movie reviews and things like that in each of these sub-menu bars. And so this is an example of building out that descendant tree. However, we don't just have mouse over events, we also have click events. You can click on the X button in each of the advertisements to get a new advertisement. You can click on the sort function in the Facebook like or comment section. But the real important thing to note here is that this descendant tree, as with all of the descendant trees in our observed collection, at the deepest, they're only 2 interaction levels deep. Meaning that in order to go from the root to the leaf nodes of our tree, we only have to execute at most 2 interactions to get there. Now, even though they're very shallow, they're actually really wide. The largest interaction tree that we saw was 7,000 descendants wide. And so that sort of is shown in this particular diagram where we're measuring the number of embedded resources required to crawl each of the interaction levels. So at our root level, we have approximately 10,000 embedded resources that it takes to capture every representation, every embedded resource at that level. But if we go just to the first level, we now need almost 54,000 additional embedded resources in order to build out and archive that level. And this gets, we need even further 10,000 more to get to those leaf nodes down at the second level. And you might be saying, well, that it doesn't matter much because these might be well represented in the archives, but they're not. So if we start at the root level again and talk about the 10,000 URIRs that are required to archive that root level, we see something that's about at the same presence level in the archives as the live web. That is, about 15% of that root level is unarchived and not represented in the archives. However, that number, again, remember that this first level is 54,000 wide. Here we're seeing that 92% of those are not present in the archives, meaning that by and large, the things required to build out that first level are not being represented and not being archived. And that gets even worse at the second level, where 96% of those about 10,000 embedded resources are not present in the archives, showing that by and large, except for the root node of our tree, these descendants are not being represented in the archives. I mentioned, and you might recall, that doing this is very expensive in time. Using PhantomJS to uncover these descendants is expensive. But we show that per second of added crawl time to your overall crawl effort, crawling down to the first level of descendants is actually going to give you your biggest return on investment at 2.3 URI hours per second of added crawl time versus the other crawl time. So if you're concerned about your crawl time, we recommend that you stop after crawling that first level of interactions. So as I've mentioned, this can be expensive in time, but it can also be expensive in space. In order to store these descendants, we propose that the archives use the IIPC proposed JSON metadata and add that to their WARCs, the web archiving file formats that they use to store this information, in order to represent the fact that we have a descendant. And that will add about 16.5 kilobytes per WARC of additional metadata. And when you consider the cost in storage space to store deferred representations, descendants, and all of their embedded resources, the archives will require about 5 times more storage than they're currently required. So that gets into the extent of the work that we've done in this dissertation, and by no means have we completely solved the problem, so we do have some area of future work. For example, because crawling is so expensive in time and in space, we want to understand the highest value targets for our crawlers. And to do that, we want to be able to simulate the most likely paths through a descendant tree that a user might take and be able to train our crawlers to take that path as well, basically identifying the highest probability of user access. We also want to understand, after doing that, what is going to be the end result of the not only quality but also completeness of the archives as a result of our two-tiered crawling approach. And we want to use, again, our D sub m and M sub m metrics in order to measure this. We also have something that I call the archival halting problem, and that is understanding when we've got enough. So with things like Google Maps that have a near infinite interaction frontier, meaning a near infinite combination of clicks, zooms, pans, and things like that, how many of those do we have to do in order to get all of the map tiles for Norfolk? Or how many times do I have to click refresh on CNN.com in order to get all of the advertisements that will ever be given to CNN.com? And finally, we have this nice proposed IIPC metadata for storing these descendants and deferred representations. And we want to write some software that will allow us to replay those descendants and those interactions from the mementos and from the archives. So in conclusion, if we go back to the 3 research questions that we posed at the beginning, we first wanted to know to what extent does JavaScript impact the archival tools and therefore the archives. And to do this, we defined a few terms. We defined the term deferred representation and zombie resources. And we showed that the adoption of JavaScript to load embedded resources correlates to missing embedded resources in our archives. And we also showed that deferred representations have reduced archivability, meaning they aren't as easy to archive as their non-deferred counterparts. Getting to research question 2, we wanted to understand how to quantify the impact that this is having. We wanted to quantify the impact this is having on memento quality. And we showed that the naive metric of percent of missing embedded resources is actually less accurate than a 50-50 coin flip. And so as a result, we created the D sub m metric to measure quality and showed that D sub m is closer to human perceived quality than is M sub m. And also showed that our deferred representations have a higher damage rating according to D sub m than do their non-deferred counterparts. And finally, we wanted to understand how we can archive and replay these deferred representations. And en route to doing that, we defined descendants and showed that the interaction trees are only 2 levels deep, and also proposed a 2-tiered crawling framework to archive deferred representations and their descendants. Now, we also showed that while this 2-tiered crawling framework is going to be more thorough and more complete, it's going to run a lot more slowly. And finally, we showed that the archives are going to require significant more storage in order to store these descendants and their deferred representations. So in summary, what we've really done is we've measured the impact that JavaScript has on the archives. We've quantified the impact on quality of mementos that JavaScript is having, and we've also measured the cost in time and in space for archiving these deferred representations. And what this does is it allows the archivists, the historians, and the decision makers to make some better decisions about how they're archiving the web. They're making better decisions about and understanding the impact that JavaScript has on their archives. And finally, what we've done is we've quantified something that everyone sort of intuitively understood, and that is that JavaScript has a negative impact on the archives. And en route to quantifying this method, we've proposed a way to overcome some of those shortcomings of our current crawling frameworks to archive these deferred representations. And at this point, I can take any questions that you guys might have. Nathan, I think, was first. I don't think I want to hear from him, but I think Nathan was first.
Based on all that you've learned and studied on archiving, if I really wanted something to not be archived, how would I put it on the web?
I don't know if I'm legally allowed to do that. So really, there's a couple things that this approach doesn't do, right? So we've talked about, okay, we can identify interactive portions, we can click and we can zoom and things like that. If our crawler is well behaved, it will obey robots.txt, and if you tell it not to touch it, it won't touch it. But not all crawlers are well behaved. I can think of three-letter agencies that probably have crawlers that aren't well behaved. But if you really want something to be hidden, you put it behind a form. So that is, you have to enter in a password, or you have to enter in your super secret username in that form and click that button, and then JavaScript will be responsible for populating that stuff. So if that is one area that is sort of hidden from this. Now there are researchers that are tackling that problem, so I don't know if my advice is going to be valid for very long. There's actually some folks in the LOCKS program, the Lots of Copies Keep Stuff Safe program, that are designing crawlers to start interacting with some of these web forms and be able to discover some of the stuff that's behind it. There are also people who have done some work in uncovering what's hidden in databases on the servers by entering random stuff into forms and being able to capture what comes back. So you can't hide, I guess is the advice. Does that answer your question?
No, but I don't think you can is the answer.
That would be my advice. I think that's as close as you can get. Let me put it that way.
One of the areas where JavaScript also poses a bit of a problem for getting an accurate representation of web pages is in testing of web applications and so forth. And I've been doing a bit of work with that, and I'm not terribly surprised at what you report on that slowdown of the crawler, because that's very consistent with what I see when I run common testing frameworks on web applications when I activate the JavaScript. But do you have any ideas for why this seems to be such a drag? Because the browsers themselves seem to be able to handle it much more quickly.
So I think there's a two-part question. The first is the reason that our method was a little bit slower than some other methods that have been proposed. So we actually modeled this finite state machine after the hypercube model from Dingturk et al. And Dingturk was designing this geometric structure that could represent these client-side states most efficiently, so that you would need the fewest number of jumps in order to get to any one state. So basically limiting the time it takes to get from root node to any state in that representation. We adapted it to a tree because we wanted to populate that entire tree, because we wanted not just to get to any given state, but we wanted to get to all the states. So if you want to operate quickly, I would recommend using the Dingturk model rather than ours, but again, it's meant for different purposes. The second part of that was that we were using headless browsing using Phantom.js, and because we need to wait for the client-side events on that headless browser to occur, we actually had to have timeouts and wait for things to happen. So I would imagine that as a web user, as a human, watching a page build out, I bet on some of the larger giant pages that are going to Facebook and pulling things in, that are going to the advertisements and pulling things in, I bet the end delivery time for the slower pages is still going to be 4 seconds, but you're seeing it built out iteratively and watching JavaScript start to populate that page rather than it all happening in the background and you not seeing it until a green light flashes and you can see something in your ping snapshot.
This is true. I can think of a few websites that I congratulate myself on if I can get in, read the content, and get out before the first noisy ad plays. So.
Yeah, and I also, my personal opinion is that content authors and advertisements that push all of the content down should be beat with a wet noodle. I think that's the most annoying thing on the web.
The flip side of that is Hairtricks is really fast.
Right. That's also true. So Hairtricks is optimized. They're designing this to operate at web scale. And 2 URIs per second is slow, but it's slow because I was executing it on my home machine using my, probably throttled internet. So Hairtricks also does a really good job of understanding how to extract that information and capture it and archive it and do it very, very quickly.
Other questions from the audience? Now's your chance to get Justin. So.
One more then. Have you run into issues with sites that have analytics enabled? Because some of the stuff I've been doing, I've been amazed at how many extra URLs are generated the moment a site turns that on, and how long some of them take to resolve.
Yes, is the short answer to that question. So basically, because we're using headless browsing and we want to understand everything that it takes to build that page, yeah, those like Google Analytics and things like that, those get caught in that trap. And even though we don't see them, it is something that's part of that page and we want to understand and know about it. So what we did is each of those analytics things has like session URIs and tokens and things that are used to track the content author or track the domain or something like that. And that creates a very unique URI. And so what we did was we actually trimmed, we studied a couple of different trim policies, but settled on the one that basically trims everything that is an HTTP after the HTTP in order to show that this is from http.google.com rather than justin.com or whatever. And these results reflect that trim policy. So these numbers are actually a whole lot larger if you don't trim it and you just take basic string comparison in order to identify whether or not your URIs are unique. I think if I want to say that at that first level, I think it was something like a 40% reduction or a 25% reduction or something like that. I wrote it down. But it's in the dissertation, but there was a significant reduction in the frontier size when we implemented that trim policy.
Meaning getting rid of the advertiser unique IDs and stuff from the URIs.
Yeah, right. So basically saying that it's http.ad.google.com/refer equals cnn.com or something like that. So we take out the refer, we take out session tokens, we take out all that kind of stuff, and this is the result that we get.
Other questions from the audience? Here we go.
When you think about combining something like that with like ad block applications to get only the content?
So we want to understand where the ads are. And another thing, so sort of what the ads do is they have these known ad servers that if something's coming in from that server, they say, we're not going to let you in, and then they don't show it. But there's a publicly available and curated list of these ad servers, so we can actually tell how many of these are ads coming in. We did some work with that. I don't know if it ended up in a paper or presentation at all, but we did some work understanding the origin of some of these embedded resources. So again, I don't think that we want to use an ad blocker software, but I think that we can use some of their same techniques in order to understand the origin of these things and understand a little bit more about it. And that could be somebody else's dissertation, right? Is to understand how prevalent these are in the archives and understand specifically how to target these advertisements that again are historically important and our crawlers are completely missing. Does that answer your question, or did I dance around that too much? Yes, sir.
So do you have a working prototype? Do you have an offline Google Maps that you can do some panning and zooming?
So we didn't have a working prototype. We used the live web when we did the experiment. Obviously, we had some of our homespun web pages that clearly you click on this button and an image pops up to test it out. But we didn't have a sandbox to use. We used the live web when we were observing it. We have on GitHub, and I can't remember the exact URI, it's in the presentation somewhere, but in GitHub we have the two-tiered crawling framework code, and really all it is the Phantom.js script that does, yeah, there it is. We have the Phantom.js script that is responsible for performing those interactions and monitoring the HTTP calls and embedded resources that are required and that kind of thing. And the other part of that is we've talked a lot about Google Maps, and ironically enough, Google Maps is actually really, really difficult for our proposed method because it has such a nearly infinite crawl frontier, right? There's a nearly infinite number of combinations of click, pan, zoom that you can do in order to interact with that representation. So as a result, what we recommend is that you have some sort of canned approach, meaning click once, zoom twice, pan left 3 times, and iterate through that canned set of interactions n number of times, where n is the number that it takes you to get everything. So for those sort of infinite frontier things, we think that you should treat those special. But for things like Bloomberg.com, where you don't have an infinite crawl frontier and you only have to mouse over a few dozen things, we think that's a little bit more applicable to the process that we're presenting here.
So did you have a way to identify whether or not you were going to need to apply that special approach?
So in our 10,000 URI set, we made sure that we didn't have things like Google Maps. And we did run across some of those that we tried to do. So for example, the one that we've been toying with is where the content authors have an interactive application for viewing art or something like that. And they overlay a div over the entire screen, and every pixel issues a call to a server to tell you that you're over that pixel, so that as you're navigating through this maze of pictures or something like that, it's basically sending every pixel's information to that server. So your crawl frontier at any given descendant is your screen size factorial to get through that, which reaches scale very, very quickly. And so for things like that, we obviously omitted them from our data set, but they would still fall under that same category of you really need a canned set of interactions to interact with that representation.
Future work.
It's somebody else's PhD.
All right. Now we'll progress to questions from the committee. Erwin, did you want to go first?
First of all, looking at this overall, you're justifying the importance of this work largely on antiquarian grounds. And I'm wondering, are there other reasons to archive the web besides, well, it's going to be interesting for future historians?
Right. This does have the feel of selling insurance. You'll be sorry one day. But I think Frank was famous for being, was he like a professional testifier, professional witness or something like that a couple times, where he was actually showing up to talk about how web archives were generated in legal cases. Because a lot of times what you'll see in these kinds of areas is, you stole my idea. Well, no, I had this idea first. Well, look, mine appears in the archive first. It's, I guess, the new poor man's copyright or something. So there's reasons for doing it like that. There's reasons of analyzing trends over time, and we demonstrated that a little bit with things like the adoption of JavaScript over time. So there are other reasons for making sure that this stuff is well preserved beyond just, hey, look, it's neat to look at this in time, this when we go back in time. The other thing that I would also cite as a reason is it's different to look at, and the one that we always use are, the two that we always use are Hurricane Katrina and September 11th. It's different to read the Wikipedia article and say that somebody flew a plane into a tower than it is to go to CNN.com on September 11th or September 12th and look at the news articles and the large font and saying everybody's panicking, look at this terrible thing that's happening, and being able to iterate through the changes to CNN.com during that crisis, and being able to understand and experience and even pick through the different news stories at your leisure, than to have a well-curated and well-edited script that somebody else wrote of their experience for you. So there is a big difference between the emotive responses that you're getting from the archives versus a textbook.
Yeah, well, that's the part I think is antiquarian, but I don't think there's a lot of money in that.
Yeah, no.
It's the legal side now, and I think somewhere in your dissertation you mentioned that there were corporations that are not the public service type that you mentioned here, that have a business based on this. And I'm wondering, is that all legal, or is there more to it?
Sure. So what those businesses are doing is they're basically selling data about that crawl, and they can turn over that crawl information and archival information to the purchaser. But basically, what they're doing is saying they're selling the ability to monitor a web page and extract data from it. So they're doing, and the reason that people pay for this is to do things like market trends, market analysis, monitor and extract data from a data service source. So they're doing it for a little bit of a different reason. But there's also Google, right? I mean, Google has developed a large empire based on ranking techniques, and they've developed crawlers around those ranking techniques. And I really think that this research could have an impact on non-archival crawlers as well, to be able to index some of this information and not just archive it, because we still have to discover it in order to be able to index it.
Do you want one question?
If you have more questions, go right ahead.
Okay, well, let me ask one more question here, and that is, you have two data sets, the Twitter set, and I guess it's the Brunelle set, is that right? And I'm wondering what these are supposed to represent. Why did you choose these two? I didn't really get a sense of the significance of these two sets, as what are they representative of?
That's a really good question. So the reason that, we had two different purposes behind the experiments that we ran. In the first one, which is our Twitter and archive pair of sets that really collapses into a single set, is we wanted to understand the difference between what people are sharing and what people are actively curating. And the reason we wanted to understand this is some of the work that Scott did showed that the things that were shared over Twitter and shared over things like Bitly actually had a lower presence, a lower rate of appearance in the archives than did things that were shared places like DMOZ and other types of data sets. So we wanted to have a good contrast for this particular study of what are people sharing and how is that being archived, and how is JavaScript impacting it versus what are the government sites doing, what are the people curating, and things like that. And then when we get to our later data set, which is the one that we use for the crawl process, we wanted to understand how that was present in the archives, so basically the archival coverage of some of these different levels and things like that. And to do that, it probably would have been skewing the data to use something that was obviously being actively curated. So what we did was if you're familiar with Bitly, which is that link shortening service, basically what they do is they take a URI-R and they come up with an alias for it and they shorten it and allow you to tweet about it. And what we did was each of those Bitlys has 6 characters, and we randomly generated those 6 characters, figured out what it pointed to, and took that as our URI that we use as our sample set. So we felt that was a little bit more of a random sample than something that was either curated by, Archive.it or something else that we could have selected. We've used other data sets too, like sampling from the Alexa Top 25, when we want to understand what the big boys are doing and how bad or good they're doing. So I think that more than answers. Is that what you're looking for?
Yeah.
More information than you wanted.
Okay, then we'll have future rounds.
All right, okay.
Sure. Can you go back to the XKCD example?
Absolutely.
I don't trust my notes on it, so